In August 1950, the grandstands at Silverstone shook under a physical wave of exhaust pressure. British racing motors had finally brought the Type 15 V16 to the start line of the Daily Express International Trophy. It was a 1.5-liter, 16-cylinder marvel, force-fed by a two-stage Rolls-Royce centrifugal supercharger. It screamed toward 12,000 RPM, producing an estimated 600 horsepower. The flag dropped. The throttle opened, and the transmission instantly shattered. The car did not move an inch. A deafening mechanical triumph collapsed into immediate public humiliation, breaking the hearts of a desperate British crowd. The V16 was designed to be the ultimate expression of post-war British engineering dominance, yet its sheer complexity made it fundamentally incapable of surviving the reality of a race. But the real story of the BRM V16 is not only the story of a broken start line, it is the story of how a racing engine made British motorsport dream, scream, and fail, and why that failure is still remembered louder than most victories. Every week, we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in a workshop in Bourne, Lincolnshire, in 1947. The story begins in a Britain that had won a global war, but was rapidly losing its industrial vanity. In 1947, the country was gripped by austerity, rationing, and a desperate hunger for national triumphs. On the race circuits of Europe, there were no British victories. The early post-war Grand Prix events were entirely dominated by Italian machinery, specifically the Alfa Romeo 158 and Maserati's straight-eight engines. British drivers were forced to compete in aging, pre-war relics, watching red cars take the checkered flag on British airfields that had been hastily converted into racetracks. To Raymond Mays, a celebrated pre-war racing driver, this was a national humiliation. Mays operated out of a modest workshop in Bourne, Lincolnshire, the former home of English racing automobiles. Alongside his brilliant but ambitious engineering partner, Peter Berthon, Mays conceived an idea that was as much a political crusade as it was an engineering project. They proposed the British Racing Motor Research Trust. The concept was simple in its rhetoric, but terrifying in its mechanical execution. They would unite the fragmented, war-weary British motor and aviation industries to build a single, world-beating Grand Prix car. It would be a cooperative national effort, funded by British industry and built by British hands, designed specifically to crush the Italians. The Grand Prix regulations of the era dictated a maximum displacement of 1.5 liters for forced induction engines. Displacement, the total volume swept by the pistons inside the cylinders, is the fundamental measure of an engine's internal capacity. The Italians were largely relying on straight-eight layouts, balancing power with relative simplicity. Peter Berthon, however, looked at the 1.5-liter limit and decided that to beat Alfa Romeo, Britain had to out-rev them. He chose an astonishingly complex layout, a 135-degree V16. A V16 is a 16-cylinder engine with cylinders arranged in two banks in a V-shape. By dividing a mere 1.5 liters of capacity across 16 cylinders, each individual cylinder held just under 94 cubic centimeters. The pistons were barely the size of teacups. The engineering logic was sound on paper. By using 16 tiny pistons, the mass of each moving part was drastically reduced. Lighter pistons meant the engine could theoretically spin faster without the internal forces tearing the block apart. Berthon aimed for a staggering 12,000 revolutions per minute, a figure that bordered on science fiction for a racing car in 1947. To fund and build this mechanical leviathan, Mays traveled the length and breadth of the country, pitching to the boardrooms of British manufacturing. His rhetoric worked. He secured backing from over 300 individual British firms, turning the BRM project into a symbol of national recovery. Rubery Owen, a massive engineering firm, provided the structural steelwork and would later play a critical role in the company's survival. Lucas was tasked with developing a bespoke ignition system, a monumental challenge given it had to deliver a flawless sequence of sparks to 16 cylinders at 12,000 RPM. But the most critical partnership was forged in Derby. Rolls-Royce, The company that had powered the Supermarine Spitfire with the legendary Merlin Aero engine was brought in to provide the induction system. Rolls-Royce did not supply a conventional racing blower. They provided a two-stage centrifugal supercharger. A supercharger, a mechanically driven device that forces dense, compressed air into the engine, is essential for making power in a small displacement motor. A centrifugal design, however, behaves differently from traditional Roots-type blowers. Derived directly from wartime aviation, the Rolls-Royce unit required immense engine speeds to generate pressure, meaning the engine would produce almost no power at the bottom of the rev range and a violent surge of power at the top. The sheer scale of this industrial cooperation quickly became a logistical nightmare. In the small workshop in Bourne, a dedicated team of mechanics had to assemble an engine from components arriving from hundreds of different factories, often machined to varying tolerances. The BRM V16 was an intricate watchmaker's puzzle, scaled up to motorsport proportions. It required 32 valves, 4 overhead camshafts, and a complex train of gears located at the center of the block to drive the accessories and the supercharger. Originally promised to the public and the press for the 1948 season, the engine remained in pieces on the workbenches as the years slipped by. The British public, having read sensationalized press reports and bought promotional booklets to fund the team, waited impatiently for their mechanical messiah. Finally, in December 1949, the engine was completed. It was transported to a freezing test house at Folkingham Airfield, a former heavy bomber base in Lincolnshire. The mechanics primed the fuel system. The starter motor engaged. When the V16 finally caught, it did not sound like a conventional motor car. It sounded like a fabric-tearing scream. The two-stage Rolls-Royce centrifugal supercharger shrieked with a high-pitched turbine whine, while the 16 tiny cylinders produced a high-frequency howl that echoed across the empty concrete runways. On the dynamometer, the numbers were terrifying. Early runs suggested the engine could produce well over 400 horsepower, with theoretical peaks pushing towards 600 horsepower at extreme boost pressures. These figures easily eclipsed the Italian Alfa Romeo 158. The motoring press declared that British engineering had triumphed. The nation believed the long, frustrating wait was justified. The block was finally cast, the supercharger was fitted, and Britain had its engine. But putting it on a test bed was one thing. Making it survive a race circuit was entirely another. A racing engine, an engine designed to survive extreme speed, heat, and the brutal limits of a rulebook, was not just a power unit. In the cramped Bourne workshop, it was a volatile sculpture of aluminium and steel that demanded absolute perfection from every British mechanic who picked up a spanner. To understand why the BRM Type 15 V16 was both an industrial masterpiece and a mechanical trap, one must look closely at what the mechanics were actually forced to assemble on their workbenches. This was not a conventional machine cast in a single Midlands foundry. It was a jigsaw puzzle of parts supplied by over 300 different British companies, each machining components to varying tolerances, which all had to mesh together perfectly in a block no larger than a standard saloon car engine. The block itself was a deeply intimidating piece of casting. To keep the car's center of gravity as low as possible for high-speed cornering, Peter Berthin had chosen a 135-degree V angle. This meant the two banks of 8 cylinders were splayed out almost flat, resembling a flattened V rather than a traditional upright block. For the mechanics standing on the concrete floor, this layout was a physical punishment. They had to lean awkwardly over a wide, complex mass of hot metal, fighting for access to the spark plugs, the carburetors, and the exhaust manifolds. Every routine check required moving around a labyrinth of beautifully machined but fiercely uncooperative British iron and aluminium. Inside the block, the engine was a watchmaker's nightmare scaled up for a Grand Prix. It featured 32 valves, 2 for each tiny cylinder, driven by 4 overhead camshafts. An overhead cam design, which locates the camshaft directly above the combustion chambers, provides precise control of the valves at high speeds, preventing them from floating or crashing into the pistons. But BRM did not drive these camshafts with a simple chain or a belt. They used a complex, heavy train of spur gears, located not at the front of the engine, but dead in the center of the block, effectively splitting the crankshaft in two. This central gear drive meant that any major adjustment to the timing or any failure of a single gear tooth required the mechanics to remove the engine from the chassis and split the entire block apart. In a quiet, well-lit factory with infinite time, this was a testament to British precision. In a dusty, oil-stained pit garage with 45 minutes until the flag dropped, it was a logistical disaster. Getting the engine to fire smoothly was an entirely separate crisis. Lucas, the famed British electrical supplier, was tasked with building the bespoke ignition system. An ignition system, the network of coils, distributors, and spark plugs that ignites the fuel-air mixture, usually has a comfortable margin of error on a road car, but the BRM required 4 separate distributors to fire 16 spark plugs in a flawless, rapid-fire sequence at 12,000 RPM. If the timing was off by a fraction of a millisecond, the engine would misfire, violently throwing its delicate internal balance out of synchronization. The mechanics spent hours simply trying to tune the distributors, listening to the exhaust note in the workshop to detect the slightest hesitation in any of the cylinders. But the true defining feature of the Type 15, the element that gave it its terrifying voice, sat at the front of the block. Rolls-Royce had delivered a 2-stage centrifugal supercharger. A supercharger, a mechanically driven pump that forces compressed air and fuel into the engine, allows a small displacement block to burn much more fuel and produce massive power. However, unlike traditional Roots blowers used by the Italians, which pushed a steady volume of air at all engine speeds, a centrifugal design behaves differently. Derived directly from wartime aero engines like the Rolls-Royce Merlin that defended British skies, it acted more like a turbine, throwing air outward at immense velocity. The faster it spun, the more exponentially it compressed the air. And the V16 was designed to spin to a mind-bending 12,000 RPM. At full tilt, the Rolls-Royce blower delivered up to 72 pounds per square inch of boost pressure. Boost, the measure of forced air pressure above atmospheric normal, dictates how violent the combustion will be. Most Grand Prix racing engines of the era ran on perhaps 15 to 20 psi. The British engineers were forcing 72 psi into cylinders no larger than teacups. It was a level of pressure that threatened to blow the cylinder head straight off the block, putting immense strain on the head gaskets and securing studs. When bolted to the dynamometer in the testing house, the physical reality of this pressure became frighteningly clear. The air-fuel mixture was compressed so violently by the supercharger that the massive SU carburetors and intake manifolds would frost over with thick white ice condensation, even in a warm room. Meanwhile, mere inches away, the exhaust pipes glowed an incandescent cherry red from the sheer heat of combustion. The cooling system, a vital network of water jackets tasked with moving coolant through the labyrinth of 16 hot cylinders, struggled desperately to shed the immense thermal load, constantly threatening to boil over. To prevent the pistons from melting under extreme detonation, the engine demanded a highly specialized, highly toxic aviation fuel, blending methanol, benzol, and other heavy additives. It burned fuel at an astonishing rate, requiring a massive fuel tank that drastically altered the handling of the car as it emptied lap by lap. Yet when the timing was perfect, the coolant flowed, and the spark plugs fired in unison, the dials on the dyno confirmed the miracle. The engine could produce nearly 600 horsepower from just 1.5 liters of displacement. No other racing machine on Earth could match its specific output. The engineering was brilliant inside the workshop. The industry had built exactly what was asked, but out on the track, the V16 was about to face the ruthless reality of garagiste economics and racing physics. To understand the sheer cultural weight of the BRM Type 15, one must step out of the claustrophobic, oil-stained confines of the Bourne workshop and stand on the sunlit grass banks of a British race circuit in the early 1950s. The engine was no longer a theoretical watchmaker's puzzle bolted to a dynamometer. It was a physical weapon sitting on the tarmac at Goodwood and Silverstone. For the British public, who had endured years of post-war austerity, rationing, and the monotonous sight of red Italian cars dominating their home soil, the arrival of the V16 in the pit lane was a moment of profound national vindication. The crowds that packed the perimeter fences were not merely motorsport enthusiasts. They were factory workers, machinists, and ex-servicemen who had bought promotional booklets and donated shillings to the British Racing Motor Research Trust. They had come to see if their fragmented industry could still build the fastest machine on Earth. In the pit garage, the reality of running the V16 was an orchestrated mechanical violence. Starting the engine was not a simple turn of a key, it was a high-stakes ritual. The mechanics had to connect a portable, external starter to the front of the block. As the starter motor whined, the SU carburetors were primed with a highly toxic aviation fuel blend, heavily laced with methanol. When the 16 tiny cylinders finally caught, the exhaust pipes instantly spat fire, and the paddock was engulfed in a deafening, high-frequency scream. The sound of the BRM V16 has become a cultural ghost in British motor racing memory, but in 1950 it was a physical shockwave. Because of the 16 cylinders and the two-stage Rolls-Royce centrifugal supercharger, the exhaust note was entirely unique. At idle, it was a harsh, erratic mechanical clatter. But as the driver blipped the throttle and the revs climbed toward 12,000 RPM, it transformed into a piercing, ear-splitting shriek that physically rattled the corrugated iron roofs of the pit garages. It was the rhythm of national hope, broadcast at a volume that terrified anyone standing within 50 feet of the exhaust stacks. In a Britain where a racing engine could decide whether a nation regained its pride or exposed its exhaustion, power was not an abstraction. It was metal, highly compressed fuel, deafening sound, extreme heat, and the desperate hope of the mechanics trying to keep 16 cylinders firing in perfect time. When the car finally took to the track, the sheer numbers became terrifyingly real. Alfa Romeo had ruled the era with their legendary 158 and 159 Alfetta straight-8 engines, which eventually produced around 400 horsepower. The BRM V16, from the exact same 1.5-liter displacement limit, was capable of an estimated 600 horsepower at 72 psi of boost. On the long hanger straight at Silverstone, the V16 possessed a straight-line speed that simply defied the era's tire and chassis technology. Legend dictates that when the Italian engineers from Alfa Romeo and Ferrari first heard the BRM howling across a British airfield circuit, they felt a genuine sense of dread. The sheer auditory violence and the visible acceleration of the green car suggested that the British cooperative had actually done the impossible. The Midlands foundries, the Rolls-Royce aviation engineers, and the Lincolnshire garagists had combined to build an engine that made the dominant Italian machinery look briefly underpowered. But raw horsepower, generated on a straight piece of tarmac, was only a theoretical advantage. To translate that deafening sound into a Grand Prix victory, the engine had to be controlled through the corners by a human being. And as the greatest drivers in the world were about to discover, taming the V16 was like trying to steer an explosion. In 1952, British Racing Motors managed to secure the services of Juan Manuel Fangio, the reigning world champion, to try and tame the Type 15. Even for a driver renowned for his preternatural car control and smoothness, the V16 was a terrifying prospect. The fundamental problem was not a lack of power, it was the violent manner in which the engine delivered it to the tarmac. A naturally aspirated engine, an engine that draws in air in normal atmospheric pressure without the aid of a supercharger, builds its power in a predictable linear curve, allowing the driver to naturally sense the limit of the tires. But the BRM's two-stage centrifugal supercharger behaved like a violent light switch. Below 7,000 RPM, the tiny 1.5-liter block produced very little torque. It felt heavy, sluggish, and unresponsive. However, the moment the tachometer needle crossed 9,000 RPM, the Rolls-Royce supercharger reached its optimal efficiency, forcing a massive 72 psi of boost pressure into the cylinders. The power output did not just rise, it detonated, instantly surging from a modest crawl to nearly 600 horsepower. In a low-grip era with narrow cross-ply tires, stiff sidewalled racing rubber that offered very little traction by modern standards, this sudden arrival of power was catastrophic for stability. A driver navigating a fast, sweeping corner at Goodwood or Stowe Corner at Silverstone would suddenly find the rear wheels spinning helplessly as the boost arrived, transforming a stable racing line into a desperate fight to catch a sliding car. To keep the machine moving forward, the driver had to dance on the throttle and constantly manipulate the heavy, uncooperative gearbox to keep the engine in an impossibly narrow power band between 9,500 and 11,500 RPM. If the revs dropped, the car bogged down. If the revs spiked too high, the rear tires melted into smoke. Keeping this delicate balance was not just the driver's burden, it consumed the entire British service network in the pit lane. The engine was incredibly sensitive to temperature and fuel mixture. If the driver let the engine idle for too long in the paddock or failed to keep the revs up during a slow formation lap, the rich aviation fuel would instantly foul the spark plugs. A misfiring V16 was an unbalanced V16, and the resulting vibrations could tear the intricate internal gear train apart. When a car limped into the pits, the mechanics had to strip the bodywork and frantically replace all 16 spark plugs, burning their bare hands on the scalding aluminum cylinder heads, racing against the stopwatch to get the car back on track. The physical toll on the driver was equally brutal. The exhaust manifolds ran straight down the sides of the chassis, radiating a relentless heat soak that cooked the driver in the cramped cockpit. Oil vapor from the massive crankcase breather sprayed backward, covering their goggles and overalls. Wrestling the heavy steering wheel while simultaneously managing a hair-trigger throttle required a level of physical endurance that left drivers completely exhausted after just a handful of laps. The engine was so highly stressed that it frequently stretched its own head studs, blowing gaskets and showering the circuit in boiling water and oil. Yet, when the timing was perfect, the coolant flowed, the plugs fired, and the driver possessed the sheer bravery to hold the throttle wide open. The BRM V16 was a spectacle of absolute British industrial might. At circuits like Albi in France or the fast perimeter roads of Goodwood, the sheer straight-line speed of the BRM was unmatched. It devoured long straights, overtaking the dominant Alfa Romeos and Ferraris with a terrifying ease. The 16 exhaust stubs produced a sound so loud that pit crews had to rely entirely on hand signals, as shouting was completely useless within 100 yards of the paddock. For the British crowds packing the grandstands, this was the moment of ultimate validation. They saw the physical proof of their national effort. They saw the Lucas electrical systems, the Rubery Owen chassis steel, the Rolls-Royce aviation induction, and the Bourne mechanics functioning as one united weapon. The V16, in these fleeting, perfect moments, proved that the fragmented British motor industry could still build the fastest, most complex racing machine on Earth. Fangio, Reg Parnell, and their contemporaries managed to wrestle the beast to victories in several short sprint races and minor Formula Libre events, where the fragility of the cooling system and the transmission were not tested over a grueling 3-hour Grand Prix distance. These brief flashes of triumph became the sustaining myth of the project. The sound of the screaming V16 crossing the finish line first at Goodwood convinced the nation that total dominance was only one minor reliability fix away. But a racing engine cannot survive on perfect conditions, endless replacement parts, and short sprint distances alone. It requires consistency, it requires reliability, and above all, it requires a stable rulebook. The British crowds cheered the deafening sound of the 16 cylinders, completely unaware that in the boardrooms of the FIA in Paris, a regulatory decision was being made that would render every drop of sweat in the Bourne workshop entirely useless. The V16 had taught Britain to build a mechanical masterpiece. It had not solved what would happen when the rules of the game changed entirely. The first crack in the BRM V16 empire did not happen in the metal of the engine block, nor did it happen on a British race circuit. It happened in a boardroom in Paris. While the crowds at Goodwood and Silverstone were still cheering the deafening sound of the 16 cylinders, the FIA, Motorsport's international governing body, was looking at a broken economic model. By the end of the 1951 season, Grand Prix racing was in a state of severe crisis. Alfa Romeo, having won the championship, abruptly withdrew from the sport, citing the immense unsustainable cost of developing their supercharged engines. With very few cars left capable of competing at the highest level, the FIA made a pragmatic, ruthless decision for the 1952 and 1953 World Championships. They abandoned the 1.5-liter supercharged formula entirely, shifting the premier class to Formula 2 regulations, which mandated 2.0-liter naturally aspirated engines. A naturally aspirated engine, one that relies purely on atmospheric pressure to draw in air, without the complex, expensive force of a supercharger, was dramatically cheaper to cast, machine, and maintain. This rule change was designed to save the sport by favoring smaller agile manufacturers, and privateer garages. But for British racing motors, it was an absolute death sentence. The Type 15 V16 had been designed specifically and exclusively to exploit the 1.5-liter forced induction rule. Overnight, the greatest, most complex engine in British history was rendered entirely obsolete for the World Championship before it had even completed a full, reliable season of racing. It was suddenly locked out of the very international arenas it had been built to conquer. The only place left for the V16 to race was in Formula Libre, an open specification category that hosted minor, non-championship sprint races. The engine that was supposed to carry the unified pride of the British motor industry across Europe was abruptly reduced to an exhibition act at local British airfields. For the British Racing Motor Research Trust, this regulatory displacement was the final blow to an already fragile financial system. The V16 was never just a piece of machinery, it was an industrial network of over 300 British suppliers. Companies like Lucas, Girling, and Rubery-Owen had donated immense amounts of time, bespoke parts, and skilled labor under the promise of national prestige and global advertising. But industrial patience is strictly tied to results. As the development dragged on for years, as the costs spiraled, and as the rules finally changed to lock the car out of Europe, the goodwill of British industry evaporated. By late 1952, the trust was bankrupt in all but name. The grand cooperative dream, the idea that a nation could build a racing car by committee, had failed. To prevent the entire project from being scrapped, liquidated, and sold for parts, Alfred Owen, the head of the Rubery-Owen manufacturing empire, stepped in and bought BRM outright. The badge remained on the nose of the car. The factory in Bourne remained open, but the system behind the engine had fundamentally changed. BRM was no longer a state-backed national crusade. It was a private racing team operating on a strict, closely monitored budget. And the V16 was the worst possible engine to run on a budget. Maintaining an engine with 32 valves, 4 camshafts, a central gear train, and a 2-stage Rolls-Royce centrifugal supercharger required aviation-level resources. In the early days, if a complex bespoke component failed, the trust could appeal to the original manufacturer to machine a replacement. Under private ownership, the Bourne mechanics had to make do. Parts scarcity became a genuine, daily threat in the workshop. When the engine inevitably broke its delicate timing gears, or when the extreme cylinder pressures stretched the head studs, the mechanics had to strip the block and rebuild it, using whatever spares they had left in the bins. The sheer manufacturing cost of replacing parts for a 16-cylinder engine meant that meaningful technical development effectively stopped. The V16 was frozen in time, an engineering monolith that could not be simplified, cheapened, or easily adapted to the changing times. The mechanics in the Bourne workshop were no longer trying to beat the world. They were simply trying to keep a mechanical dinosaur alive long enough to cross a finish line, fighting an engine that had lost its purpose the moment the rulebook changed. By 1954, the British racing paddock had fundamentally transformed. The brutal, heavy, front-engine supercharged monsters were being rapidly outpaced by a new philosophy of motorsport. A new generation of British garagistes, small, agile teams like Cooper, were beginning to mount lightweight, naturally aspirated engines behind the driver. They were using simple, reliable 4-cylinder power plants, some even derived from Coventry Climax fire pumps. These engines produced a fraction of the V16's horsepower, but they did not overheat, they did not shatter their gearboxes, and they did not require an aviation-grade logistics network to survive a Sunday afternoon sprint. The contrast in the pit lane was stark. Next to the nimble, quiet, bare-metal Coopers, the BRM Type 15 looked and sounded like a relic from a forgotten war. The Bourne mechanics were still fighting the same unsolvable equations, trying to balance 4 distributors, bleeding the complex cooling system, and praying that the central gear train would not shear its teeth under the violent surge of the Rolls-Royce supercharger. Even in the domestic Formula Libre events, the only stage left where the V16 was legally permitted to stretch its legs, the engine's inherent flaws could not be hidden. Drivers like Ken Wharton and Ron Flockhart wrestled the cars to occasional, spectacular victories at circuits like Goodwood, enveloped in tire smoke and that deafening, fabric-tearing howl. But the sheer violence of the power delivery continued to cause terrifying accidents. The throttle response was simply too unpredictable, the chassis too heavy, and the tires entirely incapable of managing the sudden arrival of 72 psi of boost. Alfred Owen, a pragmatic industrialist, looked at the balance sheets and the broken metal returning to the Bourne workshop. He realized that British racing motors could not survive on the memory of a sound. If BRM was to become a serious, self-sustaining racing team, it had to abandon the arrogant complexity that had defined its founding. It had to build a simple, reliable car. The engineering directive was given to replace the V16 with a new 2.5-liter, naturally aspirated four-cylinder engine, the Type 25. It was a humiliating, yet absolutely necessary, capitulation. The grand national dream of an unbeatable 16-cylinder masterpiece was quietly dismantled to make way for a conventional, four-cylinder reality. In 1955, the Type 15 V16 made its final few appearances. The crowd still gathered by the perimeter fences, drawn by a noise that physically vibrated through their chests. But the mechanical trust was gone. The mechanics in the pit garages no longer viewed the engine as a weapon of national pride. It was simply a heavy, dangerous burden that had consumed nearly a decade of their lives. When the V16 was finally retired, there was no grand ceremony. The remaining blocks, the intricate 32-valve cylinder heads, and the Rolls-Royce centrifugal superchargers were unceremoniously pushed into the dark corners of the Bourne workshop, covered in tarpaulins and left to gather dust. The sheer cost of running them meant they were completely useless to privateers or amateur hill climb racers. The engine was too complex to sell, too expensive to run, and too historically painful to scrap. The most ambitious racing engine in British history did not die in a blaze of international glory on a European circuit. It died because the economics of motorsport, the international rulebook, and the limits of physical grip had simply moved past it. The engine still ran. The orders stopped. The rulebook changed. The parts grew scarce. The factory moved on. The sound faded. The myth remained. The Britain it was built for was gone. British racing motors did not die with the V16. The company survived the public humiliation, learned from the brutal economic reality of the 1950s, and eventually adapted to the world that had rejected them. In 1962, a full decade after the Type 15 was rendered obsolete by the FIA, Graham Hill won the Formula One World Championship driving a BRM, but he did not do it in a screaming, supercharged 16-cylinder monster. He won the title in a BRM P57, powered by a pragmatic, naturally aspirated 1.5-liter V8. The company had finally absorbed the ruthless lesson that the V16 had taught them. In the unforgiving environment of a race circuit, extreme mechanical complexity is a liability, not an asset. But motorsport memory is rarely dictated by cold, rational championship results. The paradox of the BRM V16 is that it failed to conquer the world, yet it is remembered with far more reverence than the reliable V8 that actually secured the title. While the successful cars of the 1960s are respected as great machines, the Type 15 survives as a cultural ghost. It is a myth built entirely on sound, heat, and unhinged ambition. In the decades since it was retired, the sheer auditory violence of the V16 has become a legend within British preservation culture. Nick Mason, the drummer of Pink Floyd and a dedicated historic racer, famously took a professional recording crew to capture the exhaust note of a preserved V16 simply because no other instrument on Earth produced that specific, terrifying physical rhythm. Today, when one of the surviving cars is rolled out of a transporter and fired up at the Goodwood revival, the modern paddock stops. As the rich scent of methanol and castor oil fills the air, modern mechanics, used to the sterile, quiet efficiency of software-controlled hybrid powertrains, physically step back from the exhaust stacks. The sound still commands an absolute primal respect. This reverence is not mere nostalgia. To look at a BRM Type 15 today, whether it is sitting silently behind ropes in the National Motor Museum at Beaulieu or resting in a specialist restoration workshop, is to look at a physical monument to a vanished industrial philosophy. It is a reminder of a fleeting post-war moment when Britain genuinely believed that if they simply threw enough suppliers, enough precision gears, enough valves, and enough boost pressure at a problem, they could overwhelm the laws of physics. The V16 represents the absolute zenith of that magnificent, arrogant belief. It was the ultimate expression of engine building as a cooperative national crusade, relying on the fragmented might of the Midlands foundries, aviation suppliers, and small-town workshops. In recent years, the cultural pull of this engine has proven so strong that the Owen family commissioned the construction of 3 new continuation V16s. Built exactly to the original 1950s blueprints, modern engineers had to unearth the old Rolls-Royce supercharger drawings, cast new aluminum blocks, and try to accurately replicate the fearsome central gear train. To watch modern machinists struggle to recreate this engine with the benefit of hindsight is to realize just how absurdly difficult it was for the men in Bourne to do it 70 years ago, working on cold concrete floors with basic hand tools and slide rules. The mechanics who service the V16 for historic racing today face the exact same impossible architecture. They still have to navigate the flat 135-degree V-angle. They still have to perfectly adjust the 32 valves. They still fear the central gear train shearing its teeth under the immense load of the supercharger. The engine remains fiercely uncooperative. It requires heated oil, warmed coolant, and a heavy external starter just to wake up. It is a machine that refuses to be modernized, demanding the exact same exhausting, oil-stained dedication it required in 1950. And that is why the failure of the V16 was actually an essential step in British racing history. By collapsing under its own weight, it cured British motorsport of its obsession with extreme complexity. The trauma of the V16 project cleared the path for the garagist revolution. It proved to an entire generation of engineers that a small, dedicated team using a simple, reliable, naturally aspirated engine was the true way to dominate Formula One. The V16 died so that the minimalist brilliance of the Coventry Climax and eventually the all-conquering Cosworth DFV could live. It taught Britain that an engine does not need to be a watchmaker's puzzle to win, it only needs to finish the race. The V16 achieved exactly what Raymond Mays asked of it. It showed the world exactly what British industry was capable of building. It just turned out that what they built was a glorious, unsalvageable dead end. Somewhere in a quiet, climate-controlled British museum, an original V16 block still sits on display, the aluminium polished, the Rolls-Royce supercharger bolted to the front, waiting for a deafening, fabric-tearing sound that the modern racing world no longer has the courage to make. See you in the next video.